On October 29th, 2025, at exactly 11:15 a.m. Universal Time, an object from another star system passed closer to our Sun than Mercury ever travels, reaching speeds of 68 kilometers per second, faster than any comet humanity has ever tracked. But here's what makes absolutely no sense. Not a single telescope on Earth captured the moment. Not one observatory recorded perihelion. Not one astronomer witnessed the instant this interstellar visitor reached maximum velocity, maximum heating, maximum stress on its nucleus. For the first time in human history, we had 5 months of advance warning, 5 months to prepare every instrument we possess, and yet we were completely, impossibly blind during the one moment that mattered most. And new evidence suggests there may be a reason why we couldn't look. If you've been following the 3i Atlas story since its discovery, you already know something doesn't fit the narrative they're giving us. But if this is the first time you're hearing about what happened on October 29th, hit that like button right now, subscribe so you don't miss what we uncover next, and drop a comment telling me where you're watching from. Because in the next several minutes we're going to examine why October 29th should have been the most observed day in modern astronomy and why instead the Sun itself became an impenetrable barrier between us and the truth. Let's find out what happened when we couldn't look. Think about what I just told you. We've been tracking asteroids, comets, and near-Earth objects for decades with increasingly sophisticated technology. We can spot rocks the size of cars millions of miles away. We can predict their trajectories years in advance with mathematical precision that would have seemed like magic to previous generations. We have space telescopes positioned beyond Earth's atmosphere, satellites monitoring the Sun from multiple angles, ground-based observatories spanning every continent. We have radar systems capable of mapping the surface texture of objects hundreds of millions of kilometers distant. And yet on October 29th, 2025, when 3i Atlas, an object we'd been watching since July, made its closest approach to the Sun, we saw nothing. Not because our technology failed, not because we weren't looking, but because of where the comet was positioned relative to Earth and the Sun. Here's what astronomers expected to observe during perihelion. They anticipated measuring the exact moment of closest solar approach, calculating precise velocity changes as the comet accelerated through the Sun's gravitational well. They wanted real-time spectroscopic data showing how the nucleus responded to extreme solar heating temperatures capable of vaporizing surface ice and releasing trapped gases from deep within the comet's core. They planned to track rotational changes, looking for tumbling patterns that would reveal the object's internal structure and density distribution. They hoped to capture the moment of maximum outgassing, that brief window when the coma would expand most dramatically, potentially revealing chemical signatures invisible at greater distances. Every telescope with the capability was theoretically ready. Every astronomer who understood the significance of an interstellar visitor had marked their calendar. October 29th was supposed to be the day we finally got clear, unambiguous data about what 3i Atlas actually is. Instead, they got nothing, and the reason is as simple as it is frustrating. Solar conjunction. Let me explain what that means without the jargon. Starting around October 1st, 3i Atlas began moving into a position where, from Earth's perspective, it appeared increasingly close to the Sun in our sky. By October 21st, 8 days before perihelion, the comet had slipped behind the Sun's glare, less than 30 degrees of angular separation from the solar disk itself. For ground-based telescopes, this creates an impossible observation problem. You cannot point a telescope anywhere near the Sun without risking catastrophic damage to the instrument's optics and sensors. The light is too intense, the heat too extreme. Even space telescopes with specialized solar coronagraphs instruments designed specifically to block the Sun's overwhelming brightness struggle to observe objects that close to the solar limb. And 3i Atlas wasn't just near the Sun in our sky. It was directly behind it, precisely aligned during its closest approach. This blind spot lasted from early October through early November. For more than a month, the most interesting interstellar object we've ever tracked, with advance warning, became effectively invisible to Earth-based observation. Think about the timing. The comet reached perihelion on October 29th. Solar conjunction, that astronomical alignment that renders observation impossible, occurred on October 21st. 8 days of separation. 8 days during which the comet was hidden behind the most luminous object in our solar system, unreachable by conventional optical and infrared astronomy. 8 days when anything could have happened and we wouldn't know. Now, I need to be clear about what we did manage to observe, because this isn't a complete blackout of information. NASA's GOES 19 weather satellite, positioned in geostationary orbit with instruments designed to monitor solar activity, captured images of the comet between October 18th and October 24th. The comet appeared at magnitude 12, bright enough to register on sensors not specifically designed for deep space observation. The Solar and Heliospheric Observatory, SOHO, which sits at the L1 Lagrange point between Earth and the Sun, recorded heliospheric data during the passage. These satellites gave us something. They confirmed the comet's trajectory, verified its continued existence, provided rough brightness estimates. But they didn't give us what we needed. They couldn't perform detailed spectroscopy. They couldn't measure precise rotational dynamics. They couldn't capture the spectral signatures that would differentiate a normal comet from something more unusual. They saw the comet pass, but they didn't see what the comet was doing during passage. And here's where it gets strange. This observation gap wasn't a surprise. Astronomers knew from the moment they calculated 3I Atlas's trajectory back in July that perihelion would occur during solar conjunction. They had 5 months to plan alternative observation strategies. They could have coordinated with Mars-based instruments. Mars Express was relatively close to the comet's trajectory on October 3rd, positioned at just 0, 19 astronomical units away. They could have prioritized Space Telescope time during the brief windows before and after conjunction. They could have positioned solar observation satellites for optimal viewing geometry. But for reasons that remain unclear, none of these alternative strategies were implemented at scale. When October 29th arrived, we were watching from behind a wall of solar radiation, and the most important moment in 3I Atlas's journey through our solar system happened in complete observational darkness. That's not bad luck. That's not oversight. That's the inevitable consequence of orbital mechanics and the geometry of our solar system. But it leaves us with a question that nobody's answering. What happened during those 8 days when we couldn't see? We need to talk about how much time we had. Because when I say we were unprepared for October 29th, I don't mean we were caught off guard. This wasn't like Oumuamua in 2017, when we discovered the object only after it had already passed perihelion and was racing away from the Sun at hyperbolic velocity. That discovery shocked the astronomical community precisely because we had no warning, no opportunity to position instruments for optimal observation, no chance to plan coordinated campaigns across multiple observatories. We spotted Oumuamua on October 19th, 2017, and by the time we realized it was an interstellar object rather than a solar system asteroid, it was already outbound, already fading, already slipping beyond the reach of detailed spectroscopy. We got one chance, and we missed most of it. But 3I Atlas was different. We had 5 full months, from the moment Atlas survey telescopes in Chile detected the object on July 1st, 2025, at magnitude 18 dim enough to require sensitive instruments, but bright enough to track with modern equipment. The astronomical community knew something unusual was approaching. Initial orbital calculations placed it on the Near-Earth Object Confirmation page, that digital clearinghouse where preliminary observations get refined as more data accumulates. Within weeks, additional observations from multiple observatories around the world allowed for trajectory refinement. By mid-July, the verdict was clear. This object wasn't bound to our solar system. Its orbital eccentricity, that measure of how elliptical or hyperbolic a trajectory is, exceeded 1.0. In gravitational mechanics, an eccentricity above 1, 0 means the object is on an escape trajectory. It arrived from interstellar space, and it will return to interstellar space after its brief visit. We were watching humanity's third confirmed interstellar object. Let me give you context for why that matters. Oumuamua, discovered in 2017, entered our solar system with a hyperbolic excess velocity of about 26 kilometers per second. That's the speed it carried beyond what our Sun's gravity alone would provide the velocity it brought with it from interstellar space. It was fast, unusual, and tumbling in ways that suggested either an elongated shape or something we didn't understand about its mass distribution. Then, in 2019, we discovered 2I/Borisov, the second confirmed interstellar visitor. Borisov arrived with a hyperbolic excess velocity of roughly 32 kilometers per second, faster than Oumuamua but still within ranges that matched theoretical predictions for how objects move through the galaxy. Borisov behaved like a comet outgassing, developing a visible coma, exhibiting spectral signatures consistent with solar system comets. It was weird because it came from another star, but it wasn't weird in how it behaved once it got here. 3I Atlas is different. Its hyperbolic excess velocity at perihelion reached approximately 58 kilometers per second. Let that number sink in for a moment. It's moving nearly twice as fast as Oumuamua, almost twice as fast as Borisov. This isn't just unusual, it's at the extreme edge of what we expect from objects drifting through interstellar space. Faster speeds suggest either a more energetic ejection from its origin system, or a trajectory shaped by gravitational interactions we don't fully understand, or something else entirely. Speed matters because it affects how the object interacts with our sun's gravity, how much time we have to observe it, and what kinds of stresses the nucleus experiences during perihelion passage. A comet moving at 68 kilometers per second during closest solar approach is experiencing gravitational and thermal forces that would tear apart a loosely bound rubble pile. Whatever 3I Atlas is, it has to be structurally coherent enough to survive that passage intact. By September 2025, astronomers had refined the trajectory to extraordinary precision. They knew perihelion would occur on October 29th. They knew the closest approach distance would be approximately 36 astronomical units from the Sun inside Earth's orbit, but not dramatically so. They knew the comet's path would carry it almost perfectly along the ecliptic plane, that flat disk where planets orbit, coming in at a steep inclination of about 175 degrees. That inclination meant the comet was travelling retrograde, moving backward relative to the direction planets orbit. Retrograde orbits aren't impossible, but they're uncommon among solar system objects, and they suggest an origin far from the gravitational influences that shape typical comet reservoirs like the Oort cloud. This was an outsider, something formed in conditions utterly unlike the environment that birthed our planets. They also knew, by September, that solar conjunction would blind us during perihelion. The trajectory calculations made it obvious. On October 21st, the comet would slip behind the Sun from Earth's perspective, entering a zone of solar elongation less than 30 degrees too close for safe optical observation, and it would remain in that zone through early November, long after perihelion had passed. Every astronomer reviewing the data understood the problem. They had months to prepare alternative observation strategies, to coordinate with spacecraft positioned elsewhere in the solar system, to prioritize this object above routine surveys and scheduled observations. But institutional inertia is a powerful force. Telescope time is allocated months in advance. Space missions operate on tight schedules with competing priorities. And perhaps most importantly, 3I Atlas was classified, despite its unusual speed and trajectory, as an active comet interesting, but not extraordinary enough to justify disrupting established observation plans. So we watched it approach. We tracked its brightness as it moved closer to the Sun, growing from magnitude 18 in July to magnitude 12 by October. We collected spectroscopic data when weather and telescope availability permitted. We built models of its orbit, refined predictions, published papers on its composition and activity levels, and then October arrived. The comet slipped behind the Sun, and all that preparation became useless. The moment we'd been tracking for 5 months happened in the one place we couldn't observe. Now let's talk about what makes 3I Atlas resist easy classification. Because if this were simply a fast-moving comet from another star system, interesting but ultimately conventional, we wouldn't be having this conversation. The observations we have the data collected before solar conjunction rendered the comet invisible contain patterns that don't fit comfortably into standard comet science. I'm not talking about wild speculation or fringe theories. I'm talking about peer-reviewed findings, measurements taken by credible institutions using state-of-the-art instruments, analysed by astronomers who have no interest in sensationalising their work. These are the anomalies that show up in the data, whether we want them there or not. Start with polarisation. When light reflects off a comet's nucleus and coma, it becomes polarised. The electromagnetic waves align in specific orientations depending on the surface composition, particle size distribution, and scattering geometry. Astronomers measure this polarisation to infer properties they can't observe directly, like whether the nucleus is icy, rocky, or covered in organic compounds. It's a standard diagnostic tool, applied to thousands of comets over decades of observation. We have excellent baseline data for what normal comet polarisation looks like, and 3I Atlas doesn't match that baseline, not even close. The polarimetry measurements taken before solar conjunction revealed extreme negative polarization, a characteristic more commonly associated with trans-Neptunian objects, those distant primordial bodies orbiting in the frozen outer reaches of our solar system, than with active comets. Negative polarization suggests surface properties fundamentally different from the dusty, icy mantles typical of solar system comets. Among the more than 10,000 comets observed with polarimetric techniques, 3I Atlas sits at the extreme outlier end of the distribution. That's not just unusual, it's unprecedented. Mainstream astronomers attribute this to specific mineral compositions in the nucleus or unusual dust properties in the coma. But they also admit it's strange, something requiring explanation rather than fitting comfortably into existing models. When your object behaves more like a Kuiper belt object than a comet, despite exhibiting clear cometary activity like outgassing and coma formation, you've got a puzzle that doesn't resolve easily. Then there's the chemistry. NASA's James Webb Space Telescope turned its infrared instruments toward 3I Atlas during approach, capturing spectroscopic data that revealed the comet's chemical composition with extraordinary detail. What they found was both familiar and unsettling. The comet contains water ice, water vapor, carbon monoxide, carbon dioxide, and carbonyl sulfide, all compounds we've seen in solar system comets. But the ratios are wrong. 3I Atlas is unusually rich in carbon dioxide, containing proportions that exceed typical comet averages by significant margins. It's also emitting cyanide gas and atomic nickel vapor, both detected through their characteristic spectral signatures. Cyanide isn't rare in comets, it's a product of organic chemistry in icy bodies. But nickel vapor is less common, suggesting either unusual metal content in the nucleus or heating patterns that vaporize metals more readily than expected. This chemical signature tells us something about where 3I Atlas formed. The abundance of carbon dioxide suggests formation in a colder, more carbon-rich environment than the region where our solar system's comets originated. Different star systems have different elemental abundances depending on the supernova generations that seeded their formation. If 3I Atlas comes from a system enriched in carbon, its composition makes sense, but it also marks this object as chemically distinct, a visitor carrying the fingerprint of alien stellar chemistry. When you analyze its spectrum, you're not just seeing a comet, you're seeing the echo of a different star's planetary formation history. Now we get into more controversial territory. There are claims circulating in independent astronomy communities, unverified by mainstream observatories, but persistent enough to warrant mention that 3I Atlas exhibits unusual emission patterns. Specifically, some observers report detecting pulse signals in the 1.42 GHz frequency range, arranged in what appears to be a Fibonacci sequence, 81385-138. If true, this would be extraordinary. The first, 42 GHz frequency corresponds to the spectral line of neutral hydrogen, the most abundant element in the universe, and a frequency SETI researchers have monitored for decades on the assumption that any advanced civilization would recognize its significance for interstellar communication. A signal at this frequency, organized in a mathematical pattern like the Fibonacci sequence, would be nearly impossible to explain as natural outgassing or random emission. But I need to emphasize, these claims remain unverified. No major observatory has published confirmation of this pattern. No peer-reviewed paper has validated the methodology used to detect these pulses. We're in speculative territory here, relying on reports from amateur astronomers and independent researchers whose work hasn't survived institutional scrutiny. Maybe they're seeing something real that mainstream instruments missed. Maybe they're seeing noise and interpreting pattern where none exists. Right now, we don't know. What we do know, with certainty, is the orbital trajectory. 3I Atlas arrived on a hyperbolic path with an eccentricity of 6.137, higher than any previously confirmed interstellar object. High eccentricity means the trajectory is strongly hyperbolic, less curved, more of a straight-line passage through the solar system with a sharp gravitational deflection at perihelion. The comet's path also carried it nearly aligned with the ecliptic plane, that flat disk where planets orbit, despite approaching at a steep inclination of roughly 175 degrees. This combination retrograde motion, ecliptic alignment, extreme eccentricity is mathematically possible, but statistically rare. Random objects drifting through interstellar space can approach from any direction with any trajectory. The fact that 3I Atlas came in almost parallel to the plane of planetary orbit strikes some astronomers as coincidental. Others see it as inevitable, given the vast number of potential interstellar objects passing through the galaxy. Interpretation depends on whether you think one unusual case proves a pattern, or whether you need multiple examples before drawing conclusions. Then there's the size uncertainty. Estimates for the nucleus diameter range from as small as 0.32 kilometers to as large as 5.6 kilometers, with most analyses suggesting a diameter less than 1 kilometer. That's a huge range of uncertainty for an object we've been observing for months. The problem is brightness doesn't directly translate to size unless you know the object's reflectivity, called albedo. A small, highly reflective object can appear as bright as a large dark object. Without direct imaging resolution sufficient to measure the nucleus's actual dimensions, we're forced to infer size from brightness and assumptions about surface properties, and those assumptions might be wrong. If 3I Atlas has an unusually high albedo, perhaps due to surface ice or reflective mineral coatings, it could be much smaller than the brightness suggests. Smaller size creates a different problem. How does a sub-kilometer nucleus produce the observed outgassing levels? Comets outgas when solar heating vaporizes surface ices, but the rate of outgassing depends on surface area and internal heat retention. A smaller comet with high activity levels implies either unusually volatile ices or a composition we don't fully understand. Put all these anomalies together, polarization, chemistry, possible emissions, trajectory, size uncertainty, and you get an object that resists comfortable categorization. Mainstream astronomers handle this by saying, comets are diverse, outliers exist. 3. I Atlas is unusual but not inexplicable. They point to other comets with odd properties, like Hale-Bopp's surprising brightness, or Comet ESO-N's fragmentation behavior, as proof that the category comet contains more variation than we sometimes acknowledge. And they're right. Anomalies don't automatically mean non-natural origin. But these particular anomalies, clustered in one object moving faster than almost anything we've seen, arriving from interstellar space on a trajectory that happened to hide it during perihelion, that combination makes some people ask whether we're looking at all the possibilities. Let's examine the two competing frameworks for understanding what 3I Atlas actually is. Because this is where intellectual honesty requires presenting both sides without tipping the scale prematurely. You need to see the evidence each interpretation handles well and where each struggles, so you can make your own judgment about which explanation fits the data more comfortably. I'm not here to tell you what to believe. I'm here to show you why this debate exists in the first place. The mainstream interpretation is straightforward and parsimonious. 3I Atlas is an active comet from another star system, ejected from its origin through gravitational interactions, perhaps a close encounter with a giant planet or perturbations from passing stars that destabilized its orbit. It drifted through interstellar space for hundreds of thousands or millions of years until its trajectory happened to intersect our solar system. As it approached the Sun, solar heating vaporized surface ices, producing the coma and outgassing we associate with comets. Its unusual speed is high, but not impossible. Objects ejected from other star systems can carry significant velocities depending on their origin circumstances. The chemical composition, rich in carbon dioxide and containing unusual ratios of volatiles, simply reflects formation in a different stellar environment with different elemental abundances. The extreme negative polarization, while rare, can be explained by specific mineral compositions or dust properties we haven't fully characterized yet. Every anomaly has a plausible natural explanation that doesn't require invoking extraordinary claims. Comets are diverse. Interstellar comets even more so because they sample formation conditions across different stars. 3I Atlas is interesting, scientifically valuable, and worthy of continued study, but ultimately it's a comet. This interpretation has significant strengths. It aligns with Occam's razor, the principle that simpler explanations requiring fewer assumptions should be preferred until evidence forces us toward more complex models. It handles the bulk of the observational data comfortably. Brightness variations, spectroscopic signatures, outgassing rates all match cometary behavior we've documented in thousands of solar system objects. It doesn't require postulating unknown physics or invoking non-natural origins. And importantly, it's the consensus view among institutional astronomers who've reviewed the data. When NASA describes 3I Atlas in official communications, they call it an interstellar comet. Full stop. No caveats, no speculation, no acknowledgement that anything unusual requires deeper investigation beyond standard cometary science. But there's another interpretation, championed most prominently by Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of Harvard's astronomy department. Loeb isn't a fringe figure. He's published hundreds of peer-reviewed papers, advised dozens of graduate students, and built a career studying black holes, cosmology, and the early universe. He's also become the most visible advocate for taking seriously the possibility that some astronomical anomalies might indicate technological artifacts rather than natural phenomena. And 3I Atlas, in Loeb's analysis, exhibits 9 distinct anomalies that, taken together, resist comfortable classification as a typical comet. Loeb's framework doesn't claim certainty. He explicitly acknowledges that extraordinary claims require extraordinary evidence, and that evidence for 3I Atlas remains incomplete. But he argues that dismissing anomalies simply because they're uncomfortable is bad science. Let's look at his 9 points. First, the extreme negative polarization, unprecedented among active comets. Second, the unusual chemical composition, particularly the high carbon dioxide abundance. Third, the trajectory alignment with the ecliptic plane despite retrograde motion. Fourth, the extraordinarily high speed 68 km per second at perihelion. Fifth, the size to brightness ratio, suggesting either unusual albedo or non-standard surface properties. Sixth, the timing of solar conjunction during perihelion, preventing Earth-based observation at the critical moment. Seventh, the reported but unverified emission patterns at 1.42 GHz. Eighth, the proximity to Mars on October 3rd, just weeks before perihelion. Ninth, the comet's origin direction, which Loeb calculates as being within 9 degrees of the source direction of the famous WOW. Signal detected in 1977, a narrowband radio signal that remains unexplained after nearly 5 decades. That last point deserves elaboration because it's the most speculative and the most fascinating. On August 15th, 1977, Ohio State University's Big Ear radio telescope detected a strong narrowband signal lasting 72 seconds, appearing in a frequency range consistent with artificial transmission. The signal was so striking that astronomer Jerry Eman wrote, "Wow," in the margins of the printout. Despite repeated attempts to detect it again, the signal never occurred. Its origin remains unknown. Mainstream SETI researchers generally attribute it to a terrestrial interference source or natural astrophysical phenomenon we don't fully understand. But Loeb's analysis suggests that 3I Atlas originated from a region of sky only 9 degrees away from the WOW, signal's source direction. He calculates the probability of this alignment by chance as approximately 0.6% low, but not impossibly low. If you have 100 interstellar objects, you'd expect one to align this closely with any given point in the sky just by random chance. But it's the kind of coincidence that makes you pause. Loeb's hypothesis isn't that 3I Atlas is definitively artificial. He frames it more carefully. Could this object exhibit signatures consistent with a technological artifact, perhaps an autonomous probe or a derelict spacecraft tumbling through space? Could some of the anomalies, especially the polarization and possible emission patterns, indicate engineered materials rather than natural ice and rock? He emphasizes that resolving this question requires better data, particularly the observations we didn't get during perihelion because of solar conjunction. But he also argues that science advances by investigating outliers, not by explaining them away prematurely. The tension between these interpretations comes down to how you weight anomalies. If you believe comets are diverse enough that any single anomaly can be accommodated within natural variation, then 3I Atlas is just an unusual comet. But if you think the clustering of multiple anomalies in one object deserves closer scrutiny, especially when the object also happens to be hidden during its most revealing moment, then you start asking different questions. You start wondering whether our categorical framework, natural versus artificial, is too rigid, whether hybrid possibilities exist that we haven't considered. What if 3I Atlas is a natural comet that happened to pass through a region of space containing technological debris, accumulating surface coatings or embedded fragments that alter its observational signatures? What if it's an ancient artifact, launched millennia ago by a civilization long gone, now defunct and tumbling through space looking identical to a comet, except under close spectroscopic examination? These questions can't be answered definitively with current data. That's the frustrating reality. We have suggestive anomalies, but no smoking gun. We have competing frameworks that handle different subsets of data better than others, and we have an observation gap during perihelion that prevents us from obtaining the very measurements that might resolve the debate. Either explanation, natural comet, or technological artifact remains possible. But the possibility itself, the fact that we're even having this conversation with peer-reviewed research supporting both sides, tells you something important about where we are in understanding what moves through the galaxy. Here's where we confront the central mystery that makes 3I Atlas more than just another astronomical curiosity. The timing of solar conjunction relative to perihelion wasn't bad luck, and it wasn't an oversight by astronomers who should have planned better. It was the inevitable consequence of the comet's trajectory, predetermined from the moment 3I Atlas entered our solar system, locked into place by orbital mechanics that couldn't be altered without invoking forces we didn't observe. And that inevitability raises a question nobody wants to ask directly. If you were designing a trajectory to pass through our solar system, while remaining unobservable during the most revealing moment, could you do better than 3I Atlas's actual path? Let me walk you through the geometry so you understand why this matters. On October 21st, 2025, 8 days before perihelion, 3I Atlas crossed behind the Sun from Earth's perspective. The technical term is solar conjunction, the moment when an object's angular separation from the Sun, as viewed from Earth, becomes so small that observation becomes impossible without pointing telescopes dangerously close to the solar disk. For 3I Atlas, this conjunction wasn't brief. Starting in early October, the comet's solar elongation dropped below 30 degrees, entering a zone where even advanced space telescopes struggle to collect useful data. By October 21st, elongation reached minimum. The comet positioned almost directly behind the Sun, and it remained in that observational dead zone through early November, more than a week past perihelion. Think about what perihelion means for a comet. It's the moment of maximum solar heating, when the nucleus experiences temperatures capable of vaporizing subsurface ices and driving outgassing rates to their peak. It's when thermal stress can fracture the nucleus, revealing internal structure. It's when any unusual properties, abnormal albedo, unexpected composition, surface features inconsistent with natural formation become most detectable, because the object is brightest and most active. For an interstellar visitor, perihelion is the moment when we learn what it's actually made of, how it responds to our sun's radiation, whether it behaves like objects formed in our stellar neighborhood or reveals characteristics alien to solar system bodies. Missing perihelion observation is like preparing for months to interview someone, then having them cancel at the last second. You still have the preliminary information, but you've lost the chance to ask the questions that matter. Astronomers knew this gap was coming. The trajectory calculations performed in July and refined through September made it obvious that perihelion and solar conjunction would nearly coincide. They had months to coordinate alternative observation strategies. Why didn't they? Part of the answer is institutional inertia. Telescope time is allocated through competitive proposal processes months or years in advance. Redirecting a major space telescope like the James Webb Space Telescope or Hubble toward an unscheduled target requires justification strong enough to displace already approved science programs. And 3I Atlas, despite being unusual, wasn't classified as extraordinary enough to warrant that disruption. It was fast, sure, its chemistry was interesting, but NASA's official assessment categorized it as an active comet scientifically valuable, but not unprecedented. There's also the Mars angle, which remains frustratingly under-discussed in mainstream coverage. On October 3rd, 2025, Mars was positioned at just 0.19 astronomical units from 3I Atlas's trajectory, closer than Earth would get at any point during the comet's passage. Mars Express, the European Space Agency's orbiter that's been studying Mars since 2003, carries instruments capable of observing comets from a different vantage point than Earth. If coordinated observations had been prioritized, Mars Express could have provided spectroscopic data during the period when Earth-based telescopes were blinded by solar conjunction. But as of early December 2025, no public data release from Mars Express has confirmed whether the spacecraft targeted 3I Atlas, and if so, what it observed. That silence is interesting. It might mean nothing. Data processing takes time, and ESA operates on schedules that don't prioritize rapid public disclosure. Or it might mean something worth paying attention to. What we did get from Earth orbit were fragmentary observations from satellites not designed for deep space astronomy. NASA's GOES 19, a geostationary weather satellite positioned to monitor Earth's atmosphere and solar activity, captured images of 3I Atlas between October 18th and 24th. The comet registered at magnitude 12, bright enough to appear on sensors optimized for tracking solar storms rather than distant comets. SEO-HO, the Solar and Heliospheric Observatory, sitting at the L1 Lagrange point, recorded the comet's passage through its coronagraph, an instrument designed to block the sun's overwhelming brightness and reveal the faint corona extending into space. These observations confirm the comet's existence and trajectory. They provided rough brightness measurements, but they lack the spectral resolution to reveal chemical composition in detail, the temporal resolution to track rapid outgassing changes, and the sensitivity to detect subtle features that might differentiate this object from conventional comets. So what did we miss? Start with real-time acceleration data. As a comet falls toward the sun, it accelerates predictably under gravitational influence. But outgassing can produce small non-gravitational forces. Jets of vapor escaping the nucleus act like tiny rocket engines, nudging the comet's trajectory in ways that deviate slightly from pure gravitational motion. Measuring these deviations tells you about the nucleus's rotation, the distribution of active vents, and the strength of outgassing. If 3I Atlas exhibited unusual non-gravitational acceleration too strong for its size, directionally inconsistent with random outgassing, or correlated with specific orbital positions that would be significant. But without detailed tracking during perihelion, we can only compare pre- and post-conjunction trajectories and infer what happened in between. Inference is weaker than observation. We also missed the spectral evolution during maximum heating. Cometary nuclei aren't uniform. They're layered structures, with surface ice and dust overlaying subsurface reservoirs of more volatile compounds. As the sun heats the nucleus, different layers vaporize at different temperatures, releasing gases in a sequence that reveals internal composition. By tracking spectral lines in real time during perihelion approach, you can map the nucleus's layered structure effectively doing non-invasive geology from millions of kilometers away. We got pre-conjunction spectra in September, and we'll get post-conjunction spectra in December as the comet fades. But the transition, the moment when heating peaks and the deepest volatile layers release their contents, happened behind the sun where we couldn't watch. Then there's rotation and structural stability. Comets often tumble chaotically, their rotation rates changing as outgassing jets exert torque on the nucleus. Close solar approach can stress the nucleus enough to cause fragmentation. The comet literally breaks apart under tidal forces and thermal stress. If 3I Atlas fragmented during perihelion, we wouldn't know until it emerged from conjunction, and we could compare its post-perihelion brightness and morphology to pre-conjunction baselines. A fragmented nucleus looks different. Multiple bright spots instead of a single central condensation, dispersed coma structure. Brightness decline as fragments disperse. But distinguishing fragmentation from normal fading as the comet moves away from the sun requires careful photometry and imaging we didn't collect during the critical window. The timing feels almost designed to frustrate investigation. Not intentionally designed. I'm not suggesting the comet deliberately chose its trajectory, though that's the kind of speculation we'll explore in the next section, but designed in the sense that if you mapped all possible hyperbolic trajectories through the solar system and asked which ones would hide perihelion from Earth observation, 3I Atlas's path ranks among the most effective. It approached nearly along the ecliptic plane, ensuring that conjunction would occur at small solar elongation, rather than passing above or below the sun's position in Earth's sky. It timed perihelion to occur just days after conjunction minimum, ensuring the closest approach happened deep within the observational dead zone, and it moved fast enough that the window for detailed pre-conjunction observation was narrow. By the time astronomers fully characterized its unusual properties in September, October was already arriving, and conjunction was imminent. Coincidence or consequence? That depends on how you interpret orbital mechanics. In a deterministic universe, everything that happened was inevitable from the moment 3I Atlas entered our solar system. Its trajectory, set by initial conditions and gravitational interactions, could have been calculated with perfect accuracy if we'd had perfect knowledge of its velocity and position vectors. The conjunction timing wasn't a choice, it was an outcome. But outcomes can still be convenient for some purposes and inconvenient for others. If the goal was to pass through our solar system while minimizing detailed observation during the most revealing moment, this trajectory accomplished that goal. Whether by accident or intention, we can't currently determine. Let's catalogue exactly what observations would have been possible during perihelion under normal circumstances, because understanding what we lost reveals why the solar conjunction gap is more than just an inconvenience. It's a missing chapter in the most important interstellar object story we've had the chance to document. Imagine October 29th without the sun in the way. Imagine every major telescope and space-based observatory trained on 3i Atlas as it reached maximum velocity, maximum brightness, maximum outgassing. What would they have seen? The James Webb Space Telescope, positioned at the L2 Lagrange point far from Earth, carries near-infrared and mid-infrared instruments capable of detecting thermal emission from cometary nuclei. Infrared observation penetrates the coma, the cloud of gas and dust surrounding the nucleus, to reveal the solid core beneath. During perihelion, when solar heating drives the nucleus temperature above 200 Kelvin, thermal infrared signatures become strong enough to map surface temperature distribution across the nucleus. Hotspots indicate active vents where subsurface ice is vaporizing. Cooler regions suggest areas covered by non-volatile dust mantles that insulate underlying ice. By mapping this thermal structure in real time, astronomers can infer rotation rate, identify specific outgassing sources, and estimate how much of the surface is actively sublimating versus dormant. JDWST's spectroscopic capabilities would also reveal chemical composition with extraordinary detail, distinguishing not just major volatiles like water and carbon dioxide, but trace compounds like methanol, formaldehyde, and organic molecules that tell you about formation conditions billions of years ago in another star system. All of that data unavailable because JWST, like every Earth-orbiting or Earth-trailing telescope, couldn't observe through the solar glare. The Chandra X-ray Observatory could have searched for X-ray emission from the comet. When solar wind, the stream of charged particles flowing outward from the sun, interacts with cometary outgassing, it produces X-ray fluorescence. The strength and spectrum of that emission depends on outgassing rate and solar wind density. Unusual X-ray signatures might indicate either abnormally strong outgassing or unexpected interactions between the solar wind and the comet's environment. During perihelion, when the comet is deep within the solar wind's dense inner region, X-ray emission should peak. Observing that peak would tell you how the comet responds to solar wind pressure in real time, providing a dynamic test of cometary physics. Chandra was available. The observation was feasible, but the target was behind the sun, and X-ray telescopes, like optical instruments, can't observe through the solar disk. Ground-based radio telescopes could have searched for emission at specific frequencies. I mentioned earlier the unverified reports of 1.42 GHz signals arranged in Fibonacci patterns. Setting aside whether those reports are credible, the 1.42 GHz line corresponds to neutral hydrogen, and comets do emit radio frequency signals through various mechanisms, molecular transitions, Mesa emission from excited molecules, interaction with the solar wind's magnetic field. Perihelion, when outgassing and solar interaction reach maximum intensity, is the optimal time to search for unusual radio signatures. A coordinated campaign involving multiple radio observatories Arecibo if it were still operational, the Very Large Array in New Mexico, ALMA in Chile, could have conducted sensitive searches for narrowband or patterned signals that might differentiate this object from normal comets. But radio observation also requires knowing where to point, and with the comet hidden behind solar radio noise, targeting precision suffers. Opportunities were missed. Even Hubble Space Telescope, aging but still powerful, could have contributed ultraviolet spectroscopy during perihelion. UV observation reveals excited atomic and molecular species in the coma oxygen, carbon, hydrogen that glow at specific wavelengths when energized by solar photons. The UV spectrum acts like a fingerprint of cometary activity, showing you which molecules are being destroyed by sunlight and at what rates. Comparing pre-perihelion and post-perihelion UV spectra would reveal how the comet's activity evolved, whether new volatile species emerged from deeper layers as heating intensified, and whether the destruction rates matched theoretical models for comets of this size and composition. Hubble's observing schedule is notoriously oversubscribed, but perihelion of an interstellar object is precisely the kind of time-critical event that justifies interrupting routine observations. Yet no Hubble data from October 29th has appeared in public archives, suggesting the observation either wasn't attempted or wasn't successful. What about ground-based optical telescopes? Under normal circumstances, a magnitude 12 comet at 1.36 astronomical units from the Sun is easily observable with moderate-sized telescopes. Professional observatories and even skilled amateur astronomers with high-end equipment can collect useful data, photometry tracking, brightness variations, spectroscopy at lower resolution than space telescopes, but still sufficient to detect major emission lines, imaging to resolve coma structure and search for fragmentation or asymmetries. A coordinated campaign involving dozens of observatories at different longitudes, ensuring 24-hour coverage, could have provided continuous monitoring through perihelion. Instead, the comet's position within 30 degrees of the Sun made even twilight observation risky and largely impossible. Ground-based observers were sidelined. The data gap extends into behavioral observation too. Comets can exhibit sudden outbursts, brief, intense episodes of activity where brightness spikes by several magnitudes over hours or days. These outbursts remain poorly understood, possibly triggered by sudden exposure of buried volatile-rich pockets or by structural collapses within the nucleus. If 3I Atlas experienced an outburst during perihelion, we wouldn't know. The pre-conjunction data from September shows steady activity, and post-conjunction data from December will show whatever state the comet is in now, but the transition remains invisible. Any anomalous behavior, unexpected brightening, rapid spectral changes, emergence of new chemical species would be hidden in the observational shadow. There's also the question of what Mars-based instruments might reveal. I mentioned Mars Express earlier, positioned at 0.19 astronomical units from the comet's trajectory on October 3rd. Mars rovers and orbiters carry cameras and spectrometers designed for surface geology, not deep space astronomy, but they've occasionally been repurposed for astronomical observation. During comet siding Spring's close flyby of Mars in 2014, multiple spacecraft observed the comet from Martian orbit and documented its coma composition and interaction with Mars's atmosphere. Could Mars Express, or even the Perseverance rover on the surface, have been tasked with observing 3I Atlas during the weeks when Earth was blind? Technically feasible, but it requires advanced planning and coordination between mission teams who have primary science objectives unrelated to comet observation. As of now, no public confirmation exists that Mars assets were redirected toward 3I Atlas, and no data has emerged. That absence might mean nothing, or it might mean the observations are being withheld pending detailed analysis, a possibility that fuels speculation among those predisposed to suspect cover-ups. By December 2025, the comet has faded to dimmer than magnitude 12, receding from the Sun and dimming as outgassing declines. It's still observable, but the window for high-quality spectroscopy is closing as the signal-to-noise ratio deteriorates. Comparing pre- and post-perihelion data will allow some inferences. If the chemical composition shifted, say, new volatile species appearing post-perihelion that weren't detected earlier, that would suggest perihelion heating unlocked deeper layers. If the brightness declined faster or slower than models predict, that tells you something about outgassing rates and nucleus size. If polarization measurements post-conjunction differ significantly from pre-conjunction values, that might indicate surface changes caused by thermal stress or outgassing erosion. But these inferences are indirect. They're detective work, reconstructing what happened from before and after snapshots. They're not the real-time documentation we should have gotten, and that's the frustration. We had a warning. We had capable instruments. We had the scientific knowledge to know which observations would be most revealing. And we were blocked by simple geometry, the Sun sitting between us and the target at the worst possible moment. Whether that geometry was coincidence, a consequence of natural orbital mechanics, or something more deliberate remains the unanswered question at the heart of this entire mystery, and it leads us directly into the most speculative territory of all. Now we enter the realm where evidence meets interpretation, where patterns might reveal design, or might simply be coincidence amplified by human pattern-seeking minds. I'm going to present several speculative connections that link 3I Atlas to broader questions about interstellar intelligence, technological artifacts, and the possibility that what we're observing isn't entirely natural. But I'm going to do it with every caveat clearly stated, because speculation without rigour is just fantasy, and this topic deserves better than that. What follows is the case for considering 3I Atlas as potentially more than a comet, not because the evidence demands that conclusion, but because the anomalies are suggestive enough to warrant the question. Start with the Fibonacci pattern claim. Multiple independent observers, amateur radio astronomers, citizen scientists monitoring public radio telescope data feeds report detecting pulse signals from 3I Atlas's vicinity at 1.42 GHz, arranged in a sequence matching Fibonacci numbers 8, 13, 8, 5, 13, 8. The Fibonacci sequence is a mathematical pattern where each number is the sum of the previous two, appearing throughout nature in spiral galaxies, plant growth patterns, and shell formations. It's fundamental mathematics, recognizable to any civilization that develops number theory. The 1.42 GHz frequency is equally significant. It's the emission line of neutral hydrogen, the most abundant element in the universe, and SETI researchers have targeted this frequency for decades on the assumption that any technologically advanced civilization would recognize its universality. A signal at this frequency, organized in a mathematical sequence, would be extraordinarily difficult to explain as natural outgassing or random radio emission from a comet. But here's the problem. These detections remain unverified by institutional observatories. No peer-reviewed paper has confirmed the Fibonacci pattern. No major radio telescope facility Arecibo is destroyed, but the Very Large Array, ALMA, and others remain operational, has published data supporting these claims. We're relying on reports from researchers operating outside mainstream channels, analysing data streams that may or may not have been properly calibrated, potentially seeing patterns in noise because they expect to see patterns. This doesn't mean they're wrong. History contains examples of amateur astronomers discovering phenomena that professionals missed, either because they were looking in the wrong places or because institutional conservatism dismissed early signals as artifacts. But it means we can't treat these reports as established fact. They're intriguing, suggestive, worth further investigation, but unproven. Now connect this to the WOW signal, that famous 72-second radio burst detected on August 15, 1977, by Ohio State's Big Ear telescope. The signal appeared at 1.42 GHz, the hydrogen line, in a narrowband emission characteristic of artificial transmission rather than natural astrophysical sources. It was strong about 30 times louder than background noise and appeared in only one of Big Ear's two receiver channels, suggesting a point source rather than terrestrial interference affecting both channels equally. Astronomer Jerry Eman circled the signal on the data printout and wrote "Wow" in the margin, and that exclamation has defined the mystery ever since. Despite decades of repeated observations targeting the same region of sky, the signal never occurred. Its origin remains unknown. Avi Loeb's analysis, published on his blog and discussed in academic talks, calculates that 3I Atlas's origin trajectory traced backward through space to its source direction comes within 9 degrees of the WOW signal's source region. 9 degrees is a narrow angular separation in astronomical terms, small enough to suggest potential connection, but wide enough that coincidence remains plausible. Loeb estimates the probability of random alignment at roughly 0.6%. That's low, but not impossibly low. If you examine 100 interstellar objects, you'd expect one to align this closely with any given point in the sky purely by chance. But 3I Atlas isn't just any interstellar object. It's one exhibiting multiple anomalies that resist straightforward natural explanations. Here's the hypothesis Loeb carefully constructs. Could 3I Atlas be related to whatever produced the WOW signal? If the signal originated from a technological source, a transmission from an extraterrestrial civilization, or an automated probe, then 48 years later, an object originating from the same region arriving in our solar system becomes less coincidental. The timing works. An object travelling at 58 km per second hyperbolic excess velocity could traverse the distance from nearby stars within 2030 light-years, in timeframes measured in thousands to tens of thousands of years. If launched or ejected long ago, its arrival now doesn't correlate directly with the 1977 signal, but it could indicate activity in that region of space, multiple artifacts, multiple transmission events, a pattern of interstellar presence that we're only now beginning to detect. This is deeply speculative. It requires assuming the wow signal was artificial, which remains unproven. It requires assuming 3I Atlas is either artificial or connected to technological activity, which is also unproven. And it requires accepting that the 9-degree angular alignment and the 48-year temporal separation are significant rather than coincidental. Each of those assumptions is debatable, but together they form a coherent hypothesis that explains multiple anomalies within a single framework. 3I Atlas as a probe or artifact from an extraterrestrial source, the WOW, signal as an earlier transmission from the same source or a related one, and the current observation gap during perihelion as perhaps an unfortunate consequence of orbital mechanics rather than intentional design. Except there's another layer to consider. If you were sending probes through the galaxy to study star systems, what trajectory would you choose? You'd want close solar approach to maximize gravitational assist, using the star's gravity to alter trajectory efficiently without expending propellant. You'd want alignment with the ecliptic plane to maximize encounters with planets. And you'd want to minimize observability by any emerging technological civilization in that system, because observation invites interference. A trajectory that hides the probe's closest approach behind the star, preventing detailed observation during the moment of maximum revelation would be ideal. That's not proof of design, it's a thought experiment. But 3I Atlas's trajectory accomplishes exactly that. The polarization anomaly adds another piece. Extreme negative polarization, more characteristic of trans-Neptunian objects than comets, suggests surface properties unlike typical icy nuclei. Metallic surfaces, or even surfaces coated with artificial materials, could produce this polarization signature. Natural explanations involving specific mineral compositions are plausible, but they require the comet to have formed under unusual conditions different enough from solar system comet formation that the object's interstellar origin becomes critical to explaining its properties. Or alternatively, the polarization indicates something artificial, a metallic shell, a reflective coating, a constructed surface designed for purposes we don't understand. I want to be absolutely clear. I'm not claiming 3. Atlas is an alien spacecraft. The evidence doesn't support that conclusion with sufficient strength to overcome the extraordinary burden of proof such a claim requires. What I'm saying is that the anomalies are numerous enough and clustered in ways coincidental enough that dismissing non-natural hypotheses without thorough investigation would be premature. Science advances by investigating the unexplained, not by explaining away inconvenient data to preserve comfortable models. If 3I Atlas is just an unusual comet, detailed study will confirm that, and we'll have learned something valuable about the diversity of objects formed around other stars. But if it's something else, a probe, a derelict artifact, or even a natural object carrying embedded remnants of technological activity, then discovering that requires asking the question seriously. The problem is that asking the question seriously requires data we didn't collect during perihelion. It requires the observations blocked by solar conjunction, the spectroscopy and imaging and radio monitoring that would differentiate natural from artificial with greater confidence. Without that data, we're stuck in ambiguity, debating interpretations of incomplete evidence while the comet fades into the outer solar system, dimming beyond the reach of detailed study. And that ambiguity, that frustrating gap in knowledge, brings us to the final question. What happens next? And will we ever know what 3I Atlas really is? Let me tell you what remains unknown about October 29th, 2025, and why those unknowns matter more than what we've already established. Because here's the reality. Everything I've described so far, the anomalies, the competing interpretations, the speculative connections, exists in a state of unresolved tension. We have observations that suggest something unusual, but we lack the definitive measurements that would force consensus one way or another. And that lack isn't temporary, fixable with more telescope time and better instruments. It's permanent. The moment of perihelion passed unobserved, and you can't rewind time to capture what you missed. So we're left with questions that may never be fully answered, and the weight of those questions defines how we should think about what comes next. We don't know the exact state of the nucleus during perihelion. Did the comet undergo thermal stress sufficient to cause fragmentation, splitting into multiple pieces that will gradually disperse as they move away from the Sun? Fragmentation would show up in post-perihelion observations as multiple bright condensations in the coma, or as an abnormally rapid decline in total brightness as fragments spread and fade. But distinguishing fragmentation from normal fading requires baseline measurements during perihelion that we don't have. We can compare pre-conjunction brightness to post-conjunction brightness and look for deviations from predicted models, but those comparisons are indirect. They tell us the outcome, not the process. If the comet fragmented on October 29th, we'll infer it from after effects, not from watching it happen. We don't know whether the chemical composition shifted during maximum heating. Cometary nuclei are layered, with surface ice and dust covering deeper reservoirs of more volatile compounds, carbon monoxide, methane, nitrogen, exotic ices that sublime only at higher temperatures. As the sun heats the nucleus during close approach, these subsurface layers begin vaporizing, releasing gases that weren't present in the coma earlier in the trajectory. Spectroscopy during perihelion would reveal this chemical evolution in real time, mapping which volatiles emerge at which temperatures. Post-perihelion spectroscopy, conducted now in December as the comet fades, will show us the composition after heating, but we won't see the transition. If unusual species appeared briefly during perihelion and then disappeared as the comet cooled, we'd miss them entirely. We don't know if the orbit underwent measurable deflection beyond gravitational predictions. Non-gravitational forces outgassing jets acting like tiny rocket engines can nudge a comet's trajectory in ways that deviate slightly from pure gravitational motion. For a small, active comet, these forces can be significant enough to alter the orbit measurably, but detecting non-gravitational acceleration requires precise tracking before, during, and after the forces act. We have pre-conjunction trajectory data from July through September, and we'll have post-conjunction data from December onward, but the gap during perihelion means we're missing the period when non-gravitational forces would be strongest. We can fit a trajectory model to the before and after positions and infer whether deflection occurred, but the uncertainty will be larger than if we'd tracked continuously through perihelion. Small anomalies might be hidden within that uncertainty. We don't know whether any unexpected emissions or signals occurred during the solar conjunction period. If the Fibonacci pulse patterns reported by independent observers are real, perihelion would be the most likely time for them to intensify, assuming they're related to some internal process activated by solar heating. But radio observation during that period was compromised by solar radio noise, which dominates the electromagnetic environment near the Sun. Detecting weak signals from a comet positioned behind the Sun is extraordinarily difficult, like trying to hear a whisper next to a jet engine. Even if 3I Atlas emitted something unusual, we might have missed it simply because the Sun's radio output drowned everything else out. But here's what we will know, or at least what we should know within the next few months. By December 2025, the comet has exited the solar conjunction zone and become observable again from Earth, though significantly fainter than during approach. Post-perihelion spectroscopy will reveal the comet's current chemical composition, allowing comparison with pre-perihelion measurements from September. If the volatile ratios change, more carbon monoxide, less water, different organic compounds, that tells us something about how the nucleus responded to heating. If polarization measurements shift, either returning to values more typical of normal comets or remaining anomalously negative, that informs the debate about surface composition. And if brightness declines faster or slower than models predict, that constrains estimates of nucleus size and outgassing efficiency. Mars-based observations, if they were conducted, might emerge in coming weeks or months. Data processing for planetary missions operates on schedules measured in months, not days, because calibration and validation take time. If Mars Express or any Martian surface asset targeted 3I Atlas during the period when Earth was blind, that data would provide an independent perspective on the comet's behavior during perihelion. But the absence of public announcements so far suggests either the observations weren't prioritized, or the results are still being analyzed, or more speculatively something interesting enough to warrant careful review before release was detected. Absence of evidence isn't evidence of absence, but it's worth noting. Then there's March 2026. On March 16th, 3I Atlas will pass within 0.36 astronomical units of Jupiter, closer than the distance between Earth and the Moon by a factor of 100. Jupiter's powerful gravitational field will deflect the comet's trajectory, providing a final opportunity for observation before the object exits the inner solar system and becomes too dim for detailed study. This flyby matters because any permanent changes caused by perihelion passage fragmentation, altered outgassing patterns, surface modifications will be visible during close Jupiter approach. The comet will brighten slightly as it nears Jupiter, giving observatories one last clear look before it fades into interstellar space. If we're going to definitively characterize 3I Atlas as either a normal comet or something more unusual, March 2026 is the deadline. After that, the comet races outward on its hyperbolic trajectory, moving too fast for our Sun's gravity to capture it into an elliptical orbit. Within a few years, it will cross the outer planet's orbits and enter the Kuiper Belt, dimming beyond the reach of all but the most powerful telescopes. Within decades, it will exit the heliosphere and return to interstellar space, becoming one more dark, invisible object drifting through the galaxy. If we haven't answered the key questions by then what it's made of, why its polarization is so unusual, whether the emission patterns were real, how it relates to the broader context of interstellar objects, we likely never will. The window is closing. The larger significance of 3I Atlas extends beyond this one object. Every interstellar visitor we detect teaches us about conditions in other star systems, about planetary formation processes operating in environments unlike our own, about the diversity of objects moving through the galaxy. If 3I Atlas is a comet, it's an extreme example, pushing the boundaries of what we thought comets could be. And if it's something else, if any of the speculative hypotheses hold validity, then it represents the first technologically detectable artifact from beyond our solar system. Either conclusion reshapes our understanding, but right now we're in limbo. We have enough anomalies to justify continued investigation, but not enough evidence to demand extraordinary conclusions. We have competing frameworks that explain different subsets of data, but no single framework that handles everything comfortably. And we have an observation gap during the most critical moment, a gap imposed by orbital mechanics and the sheer bad luck of trajectory alignment that prevents us from obtaining the very data that might resolve the uncertainty. So where does that leave us? It leaves us watching, monitoring post-perihelion observations as they're released, comparing them to pre-perihelion baselines, looking for changes that reveal what happened behind the Sun, waiting for March 2026, when Jupiter's gravity gives us one final chance to study this object up close, paying attention to whether Mars data emerges and what it says if it does, and asking the questions that institutional astronomy sometimes avoids, not because those questions are unscientific, but because they challenge comfortable assumptions about what we expect to find when we look up. 3I Atlas came from somewhere. It's going back to somewhere. And during its brief passage through our solar system, it behaved just strangely enough to make us wonder whether we're looking at a comet shaped by alien stellar chemistry, or whether we're looking at something built. I don't have the answer. Nobody does, not yet. But the fact that we're asking the question at all based on peer-reviewed observations and rigorous analysis tells you that something about this object doesn't fit the patterns we've learned to expect. Whether that misfit is natural variation or artificial design, we may learn by March 2026. Or we may watch the comet fade into darkness, still uncertain, still wondering what we missed on October 29th when the Sun blocked our view and the universe kept its secrets. Drop a comment and tell me, do you think we're looking at an unusual comet or something more? What observations would convince you either way? And are you ready to wait until March 2026 to find out what happens when 3I Atlas passes Jupiter and we get our last clear look? Because this mystery isn't over. It's just beginning, and you're here at the moment when we still have a chance to solve it. Let's see what comes next.